I'd like to introduce Paul Bernhardt. He'll be talking about using active experiments to see and hear the ionosphere. I've known Paul for probably over 25 years as a friend and colleague. And he's pretty ideal for this lecture. He has a unique perspective on the ionosphere. And it goes back a long way, and he's able to communicate with people. I want to give one short example. Years ago, he got the idea of putting radio beacons on satellites to probe the ionosphere, do tomography. It was novel, it was new. He wasn't sure how to sell it. So he decided to start a little bit low and talk to students and get some input to see, what they thought of his program, and we give them some ideas, fresh ideas to go forward with it. So we had a small meeting. This is hard to see, but these are pre-CEDAR students. They're about 8 years old. And the idea was if you can sell the program to 8 years old, you can sell it to anyone, specifically NRL management. And so Paul's smart, though. He doesn't want to just jump in with electromagnetic wave propagation theory with this group. You have to be a little more subtle. And so what he does is he opens with some magic. And this is a good move, right? Kids like magic, and for 8-year-olds, the words magic and science are almost synonymous, maybe for a lot of people. So he's doing his magic, and he gets them into it, right? He wins them over. He has their hearts. So now he can hit them with radio beacons on satellites. And so this is what he does here. But again, circuit diagrams for radio beacons is too much for these kids, but they do understand flashing colored lights. And so here's where he took the big leap. These weren't just red, green, yellow, blue lights. Now, the red light he called the 150 megahertz light. This one was the 450 megahertz light, and so on. So he's able to connect flashing lights, which kids understood, with radio frequencies. So I got excited, and one kid jumped up and said, "Dr. Bernhardt, are you telling us that if they fly your experiment in space, when we go out at night and look up in the sky, when the satellite goes overhead, we're going to see flashing lights?" And Paul said, "That's exactly what I'm saying. It's going to be Christmas every night for you kids." So it worked, okay? These kids loved it. They sold the program, and he has beacons flying on so many satellites you can't count them. So anyway, with that, you'll now hear the latest magic he's working on the ionosphere, Paul Bernhardt.
It's quite frightening working with Joe Huba at the Naval Research Lab. You actually don't have any idea what he's going to come up with next, and I think he did a great job on this introduction. Many of you spend a lot of your time monitoring the ionosphere, taking data for years, doing statistics, learning the essential physics of the upper atmosphere. There's a few of us, however, who have no patience. We like a quick reward, and these are the people doing active experiments. We don't wait for the Aurora to happen. We make our own Aurora. We don't wait for irregularities to form in the ionosphere. We make our own irregularities. So what I thought I'd do today is express to the audience why are we doing active experiments, and we are the few people who actually listen to the ionosphere. Most of you scatter radio waves, probe the ionosphere, but do you actually listen to it? And so that's why I named the talk Using Active Experiments to See and Hear the Ionosphere. And I'll tell you what see and hear actually mean in a few seconds. I want to also acknowledge my contributors. There's probably many more. And I was looking at this list, and if you look at the average age, it's right around 60. I mean, there are the younger people, older people. But I think, right around 60, which is my age, is where I cluster with my colleagues, Joe and Frank Juth and some of the other people here. Next slide, please. Okay, so what are we talking about? Active or remote sensing with active experiments. The active experiments include chemical releases and high-power radio waves. We enhance ionospheric measurements. For instance, with sporadic E layers, people scatter radar, do radio sounding, launch TMA trails and measure the winds in the region, do tomography. But the active experiments is really heater-excited airglow radiation. That's HEAR, H-E-A-R. That's where the HEAR comes from. And rocket exhaust seeding of irregularities. We can actually make our own sporadic E layers. I'll show you how to do that. For equatorial irregularities, airglow, backscatter, incoherent scatter, radio beacons is often used. The techniques for the active people is chemically induced electron-ion recombination. So we can actually make perturbations in the equatorial region to trigger equatorial irregularities and then artificially enhance airglow. We can brighten up the irregularities. We can actually make them easier to see. For high and mid-latitude density electron temperature composition irregularities, the standard techniques are backscatter radar and radio scintillations. The active techniques are field line irregularity glow with HF excitation, where you can look at the presence of the field line irregularities, enhance backscatter by putting a hypersonic neutral cloud streaming through the region to produce irregularities. And finally, stimulated electromagnetic emissions. That's where the SEE comes from. So what you're doing is taking high-power radio waves, interacting with the plasma, and out of the plasma comes signals. And those signals tell you what's happening in the plasma and tell you properties of the plasma. Finally, plasma wave generation and propagation, MHD waves, other waves launched by Space Shuttle ohms burns, and ionacoustic turbulence from streaming exhaust. So we're making waves in the plasma with the active experiments. Next slide, please. What kind of chemicals do you use for active experiments? Well, you use material that gives you more plasma, either through photoionization or associative ionization. You can release chemicals that grab electrons. SF6 is a good example. We're mainly talking today about chemicals that produce plasma holes through ion molecule charge exchange, and then a recombination of these molecular ions to leave a neutral region where there used to be a plasma. Finally, there's neutral wind tracers, TMA, and so forth that measure the winds in the upper atmosphere. Next slide, please. The main equipment that we use for our chemical releases is the Space Shuttle, and we use the ohms engines on the Space Shuttle. It puts out 10 kilograms of molecules per second. The molecules are carbon dioxide, H2, H2O, N2, and these are just samples of firings that we've actually had the NASA team at Houston do for us. You can fire both engines at once, one or both, or one at a time, fire them in daytime, nighttime, and see what happens to the upper atmosphere. Next slide, please. The program that I have very successfully achieved about 20 shuttle burns is called SIMPLEX, Shuttle Ionospheric Modification with Pulse Localized Exhaust. The idea is you fly the shuttle around the Earth, and then you fire the engines into a ground-based radar. And I'm seeing Mike Mandillo here. This is actually initiated with a program with Space Lab 2, funded out of NASA, but subsequently NASA lost interest in that type of experiments. And so I went to the DoD Space Test Program, and I said, can I propose to have you guys coordinate some shuttle burns for me? And they said, sure, why don't you brief it to our Space Experiments Review Board? And so then and I went in front of the board and I said, I would like you to turn the shuttle engines on for 10 seconds. And the guy said, why are you even here? I mean, we'll do that for free. So they said, if you promise never to brief us again on this experiment, we will manifest you for every shuttle flight. And because one is they get credit for doing an experiment, and it costs them absolutely nothing. So we've had marvelous coordination with firing this over Arecibo, Jicamarca, Kwajalein, and as I said, we've had about 20 burns, and some of them were the results reported yesterday in our active experiment session. Next slide, please. Then I said in another briefing to the Space Experiments Review Board, can we fire the engines and hit a satellite? And Colonel Hargis said, I will let you do this because I know you will never be able to hit another satellite. So what we do is turn on the shuttle engine and have the plume actually impact, in this case it's the EPOP satellite from Canada, which is not up there yet, or the CNOV satellite. And again, we did it, and I got a congratulatory letter from Colonel Hargis saying, I told you you'd never be able to do this. And I'll show some results from that. Next slide, please. Besides high-power radio waves, we use, besides chemical releases, we use high-power radio waves. And I'm focusing on the HARP facility up in Alaska, which is the most powerful ionospheric modification, ionospheric heating facility in the world. It has a ground transmitter power of 3.6 megawatts into an antenna with a gain of 1,000. So relative to an isotropic radiator, it looks like it's putting out 3.6 gigawatts, CW at HF, reflecting in the ionosphere. The other facility is the Arecibo facility, which is a brand new construction that's going to be online next year using the big dish, putting 600 kilowatts into the focus of the big dish, giving you an effective radiated power of 220 megawatts. The marvelous thing about Arecibo, besides all the diagnostics and the good weather, is that its conjugate point is over land. So as Joe Huber showed yesterday, you can heat here and try to see effects in Argentina. Next slide, please. What do we do when we do heating? We take a high-power radio wave, we reflect in the ionosphere, produce extremely large electric fields near the reflection point. We scatter HF radar off of field line irregularities that are produced. Next slide, please. And we have HF receivers that receive these stimulated electromagnetic signals on the ground. So you send up one single frequency, and you'll get a whole host of frequencies coming back because of plasma residences inside the ionosphere. Next slide, please. We have a UHF radar that scatters off of various turbulence, plasma waves, ion waves. Next slide, please. We have an ability to accelerate electrons. We can make our own Aurora. And making Aurora over Alaska is not a big deal, but making it over Puerto Rico is a big deal. Next slide, please. We sit on the ground and look at the artificial Aurora near these heating facilities. Next slide. Thank you. The ionospheric heating physics is quite simple, as indicated by this diagram. You first of all elevate the electron temperature, you produce a hot region, push plasma to field line, possibly make VLF ducts, and Gennady Milik, Joe Huba, other people working on that. You can make irregularities, you can sketch radars off of those irregularities. You can generate electrostatic waves, and through parametric decay, strong turbulence, make low frequency and high frequency waves. And through mode conversion, you can have electromagnetic waves coming back to you at other frequencies. You can also use these high electrostatic waves to resonate with electrons, accelerate the electrons along magnetic field lines, and make artificial aurora. Next slide, please. So let's look at what we can do with active experiments in the E layer. So what is the sporadic E layer? The most common way of seeing a sporadic E layer is use an ionogram. You see a reflection at 120, 100 kilometers altitude and with a cutoff frequency of a few megahertz. But if you'll notice, the HF waves pass through the sporadic E layer and then also reflect in the ionosphere, and you have an F region trace. So that must mean that there's holes. In other words, the sporadic E layer is a bunch of blobs that are letting the HF wave penetrate through it. What is the nature of these blobs? Next slide, please. So many people have attempted to understand this phenomenon. They've used backscatter radar, looking at what they call QP echoes, quasi-periodic structures. This is from the SEEK experiment. Rob Pfaff flew in electric field booms over and through the layers, measuring electric fields in the region. Miguel Larson releases TMA and looks at the turbulence in the neutral environment. But these are not pictures of the sporadic E layer chunks themselves. Next slide, please. We tried to do a tomography experiment. We launched a rocket, the same SEEK rocket, had receivers on the ground, and reconstructed an image of the sporadic E layer using tomography. Again, not an overly satisfying view of the layer. Next slide. We can even make our own sporadic E layers, or NASA does it. Every time they launch the space shuttle, we think probably a sporadic E layer is formed. my colleague up at NRL, Serafin Rodriguez, scheduled the operation of an HF radar in Chesapeake, Virginia. Had a receiver here, and they did bistatic scattering off of the region that penetrated through the E layer. Next slide, please. So this is the launch trajectory. The solid rockets motors burn up to 55 kilometers. Then the main engines burn all the way up through 100 kilometers altitude. And this is actually where we saw enhanced HF scatter. Next slide shows. So this is different range bands. This is times. These are the times after the launch when the rocket was actually in the E region making enhanced backscatter. And we're talking 30 dB enhancement in the backscatter from an artificial sporadic E layer from the motors. But again, this is not what a sporadic E layer looks like. We can make them, but what do they look like? What do the individual pieces of sporadic E look like? Next slide, please. Well, Frank Juth and I and my colleague, Ludmila Kagan, were at Arecibo when we were very fortunate to do ionospheric heating and have a descending layer merge with the sporadic E layer to make a very strong sporadic E layer in a heating beam, in one of these HF beams. Next slide, please. And the idea is the HF waves, here's say a model of the density. The HF waves comes and produces a standing wave on the overdense portions of the E layer, and at that point you're going to couple into electrostatic waves that accelerate electrons, and so you get airglow that sort of gives you an outline of where these layers are. And the next picture is the first Technicolor image of a sporadic E layer chunk. This is the HF beam. The red portion is where the beam actually reflects in the F region, singlet D emissions. But down here at 120 kilometers, that's what a sporadic E layer bit and piece looks like. And this experiment was done in 1998, and soon after that, the Arecibo heating facility was destroyed by a hurricane. So we're very anxious, next slide please, to have the new heating facility operating where we're putting 600 kilowatts in 3-cross dipoles at the dish, reflecting off a secondary, and having a beam go up and waiting for sporadic E season so we can, again, use this beam as a giant flashlight to illuminate the existing sporadic E layers. We also say that besides providing the structure, we can actually provide the composition of these layers, and I'll show you how to do that a little bit later. Next slide, please. One other last experiment we want to do is with the acceleration of electrons. Look at the conjugate point in Argentina. We calculate it'll take about 8 seconds for these electrons to go up and over and enter here, so we will have cameras here looking for enhanced airglow. So every time you turn on the HF facility here, 8 seconds later, you should see a brightening of the singlet D 6300 angstrom airglow at the conjugate. Next slide, please. So let's see, how do we use active experiments to study the equatorial ionosphere? We all know that bubbles are formed through a Rayleigh-Taylor instability. If you propagate a 150 megahertz wave through that, you'll get scintillations on the ground, both at 150 megahertz and 400 megahertz. Or if you sit on the ground with a red line camera, you'll see a structure that mimics the singlet D production in the ionosphere. So that's one way of looking at the regularities in the equatorial region. Next slide, please. John Makela likes to use GPS satellites, both geostationary and orbiting satellites, and as the signals pass through these darkened regions where there are these bubbles forming, he gets enhanced scintillations. And that's a marvelous way, but maybe there's other ways of studying the equatorial irregularities. Next slide, please. There's radio beacons. This is our CERTO beacon on CNOFs passing over a ground receiver, and every time it passes through some structure, you get enhanced scintillation. This is at 150, 400, and 1067 megahertz. Keith Groves likes to operate the Altair radars, do backscatter off the irregularities. He can market does the same thing. Another way of looking at the irregularities in the equatorial region. Next slide, please. But why don't we just try to make an irregularity? Why don't we just try to trigger a Rayleigh-Taylor instability by calling up NASA and say, hey, can you do a burn near Kwajalein? They, of course, say yes, because they have extra fuel. So this was a burn done back in 1999 during STS 93. Here's the Altair radar integrating through this region. Dave Heisel analyzed the data for us. Next slide, please. Showing that here is the F region peak, and this was at near sunset. Here's the burn. We did the burn here, and this actually raised the level of the bottom side of the F region. In other words, we put a little perturbation on the bottom side so that we could see if we could seed an irregularity that then would evolve into a nice equatorial bubble. Next slide, please. So we didn't have very good diagnostics, so what do? We use GPS. As Anthea Koster knows, GPS is always available, so we did a burn near Kwajalein, and we used GPS receiver on Samoa, and we found 3 regions where irregularities were seen in the GPS data. And if you draw a straight line through that, and you have a time versus latitude curve, it actually goes right back to the time and the spatial point where the burn occurred. Not conclusive, but it is consistent with the fact that our burn here may have produced the irregularities in the ionosphere that were seen as the plasma convex at about 100 meters per second. Next slide, please. This actually shows the GPS data in TC and zonal distance divided by time after burn, and you see the average velocity for the result 4 hours, 7 hours, and 5.5 hours is something like 80 meters per second convecting from the point of the release. Next slide, please. My colleague Todd Pedersen has an imager at Kwajalein. So again, we call it up STP and say, why don't you do another burn over Kwajalein? Unfortunately, Altair was not available at that time, but as the next slide shows, Todd's imager produced a wonderful brightening in a region of ongoing F region irregularities. These plumes of irregularities are actually modulating the interactions with the gas in the exhaust, so you can see an enhanced edge here from the presence of the bubbles at the equator. Next slide, please. And a little bit later, you see indeed you do get the brightening of the existing structure by the presence of the exhaust vapors from the shuttle. Next slide, please. And then Todd further looked into the data, and in the green line emissions, he saw field-aligned irregularities that were not visible before the release. So what you do is you release this chemical, it then makes molecular ions recombine, and where there's more electrons, you'll get more brightening. So you're enhancing the contrast of the existing images using this chemical release. Next slide, please. How about mid and high latitude irregularities? Next slide. My friend Elsa Talat was operating a SuperDarn radar when we made a burn over here, and he noticed a few minutes later a big enhancement of backscatter. What happened was we were flying the shuttle engine, we flew the orbiter backwards. In other words, the engines were pointed forward, we tilted down 45 degrees, and we made a hypersonic cloud of gas that impacted the top of the ionosphere. We think that then drove some turbulence instabilities in the plasma to make field-aligned irregularities that produced enhanced backscatter at this point. The burn started way over here. And the other thing is the Millstone Hill radar was scanning the region, and after the time of the burn, showed that a nice ionospheric hole was produced in the plasma too. So you can do 2 things. You make field-aligned irregularities to scatter HF radar at about 14 megahertz, and you make a perturbation in the layer itself that lasts for about a couple hours. Next slide. When we turn on the high-power radio waves up at HARP, this was actually with 1/4 of the current facility. Every time you turn it on and you see some airglow, you see modulation of the airglow. These are field-aligned irregularities that are existing there beforehand. You can scatter radio waves on this, but by using the high-power radio waves both in the red line and green line, you can actually bring out the structure. The next slide illustrates an actual movie of turning the heater off and on. This is from Dave Sintman. And every time you turn it on, you see the drifting irregularities going through the volume with the field-aligned irregularities. So it's a way of just saying, okay, let's see what irregularities are there now. And this is in the 6300 angstrom band. Next slide, please. Now, the plasma physicist in me says, let's try to generate plasma waves in the ionosphere. And this is both interesting from a plasma physics point of view and from a remote sensing point of view. Next slide, please. There are a lot of waves that are sustained in the plasma. At low frequencies, you have what is known as a fast MHD wave, which, if it's propagating perpendicular magnetic field, becomes a magnetosonic wave. But in propagating in a general direction, we just call it fast MHD. There's the alphane wave, and then there's slow MHD wave, which is a magnetized ionacoustic wave. As you increase frequency, the fast MHD wave becomes a whistler, and then it becomes electron cyclotron, and then couples into ionacoustic. The alphane wave becomes electrostatic ion cyclotron wave at the ion cyclotron frequency, and then becomes an acoustic wave, and maybe couples into an electron cyclotron wave. The slow MHD wave becomes an ion cyclotron wave. At a certain wave number, this is the wave number or inverse of the wavelength, you can have a whole bunch of frequencies in the low frequency regime and also into the electromagnetic regime with your O mode and X mode, electron plasma or Langmuir wave, and then if you get high enough or short enough wavelength, you get electron sound and the electromagnetic here. Next slide, please. If you go perpendicular to the magnetic field, you have ion Bernstein waves, lower hybrid waves, upper hybrid waves, electron Bernstein waves, and light waves. Next slide. And again, with a fixed wavelength, you can get a whole host of waves that can be produced simultaneously. The point of this is, by exciting the plasma with both chemical releases and radio waves, you get a large number of waves that can tell you what's going on in the plasma. Next slide, please. The physics behind this is quite straightforward. You have an electromagnetic wave equation. This is at a fixed frequency, omega p, which is a pump wave. This is the 5 megahertz wave you actually put into the plasma. Next slide. This then can scatter into another electromagnetic wave at omega s, which has a slightly different frequency, which has the same form of the equation, but it has a driving term with the pump wave mixing with some other fluctuations in the plasma. These are low-frequency fluctuations. Next slide, please. These low-frequency fluctuations at omega L can be ion cyclotron waves, the slow magnetosonic wave, electrostatic ion cyclotron wave. And that has another wave equation, which is then driven by mixing, by the product of the electromagnetic waves. When you mix those two components, you get a frequency that's omega L, and when you mix these two components, you get the omega S frequency. Next slide, please. So there are coupling between the ion velocities in the low frequencies to that equation, that drives this equation, and the next slide, and the electromagnetic waves in this equation coupling in across to here, from this down to here, which drives the low frequency. Next slide, please. So the bottom line is you have a parametric decay instability. You have one wave making two waves that are driven by the pump and are self-sustaining with frequency offsets given by this formula, where the electromagnetic wave that's produced is this frequency minus the low frequency. And that's what you measure on the ground. You measure this electromagnetic frequency. Since that's too complex, we just throw this into a diagram here, which is just as complex. Electromagnetic pump wave, Mo converts electrostatic waves or stays at electromagnetic wave. Parametric decays into those low frequency and high frequency waves. The high frequency wave then comes back to the ground as an electromagnetic wave, and that's what you measure on the ground, but it has a frequency offset corresponding to the frequency of the low frequency of the low frequency wave. The kind of pump waves we have in the plasma are the low frequency, the pump wave can be O mode or X mode. The low frequency waves can be these magnetosonic or alphane or Whistler modes. The low frequency electrostatic or the lower hybrid ion acoustic, ion Bernstein, and magnetosonic. And high frequency can be the electromagnetic waves coming back to you. And then high frequency electrostatic or the upper hybrid or electron cyclotron, electron Bernstein. Well, these are really complex concepts that it's more fun just to get the data and listen to them. So let's see what they sound like. We've excited in the plasma a whole host of instabilities involving the high frequency, low frequency waves, and so And these are classic instabilities that have been measured in plasma physics for a number of years. Next slide, please. How do you measure these waves? Well, one wave is to fly a rocket or a satellite through the region. Next slide, please. So we have a satellite called EPOP, which will be launched next year, that has 8 sensors on it, one of which is a plasma wave receiver. This is a Canadian satellite that will fly through the region and measure in situ the wave turbulence. The next slide shows actual measurements from a 1996 launch out of Puerto Rico that Paul Rodriguez, Carl Schaefer, and myself did. And this is a rocket flying through the interaction region of the Arecibo heater, where you're measuring in situ the plasma density structures, and this showed actually a lot of cavities, and inside the cavities are trapped the electron plasma waves, the Langmuir waves, and then also in the same cavities are trapped the ion acoustic waves. So we have a pump wave at 5 megahertz or 5.1 megahertz, which is in parametric decaying into the low frequency ion acoustic wave and the high frequency electron plasma wave. Next slide, please. But we can't afford rockets that often. The satellites aren't launched yet. So why don't we just sit on the ground and listen to the emissions coming from the plasma and try to understand what physics is going on. This is the basis for stimulated electromagnetic emissions. These are generated by high-power radio waves through mode conversion on field line irregularities and parametric decay into the 2 modes I showed earlier. The ones I'm highlighting are the stimulated Brillouin generating acoustic waves, which gives you the electron temperature in the plasma. So this is a diagnostic of how hot the electrons are getting when you heat the plasma. Stimulated Brillouin also gives you electrostatic ion cyclotron, which provides the ion mass. So we can use the high-power radio waves to give you composition of the ions in the plasma. Finally, stimulated ion Bernstein waves tell you when you're getting electron acceleration. Next slide, please. The most common stimulated electromagnetic emission comes from a very complex process. It's the field line irregularity conversion of electromagnetic waves into upper hybrid waves, parametric decay into a lower hybrid, another upper hybrid, that decays into another lower hybrid, and upper hybrid, and then these convert into electromagnetic waves on the ground. Next slide. The spectra for those waves, besides the pump wave, is something called downshifted maximum. You can see a cascade of waves that are offset by 4 to 8 kilohertz from the pump frequency, and this is the indication of lower hybrid waves in the media. There's also the upper hybrid, the upshifted maximum and the broad upshifted maximum, which is a complex process involving electron Bernstein waves. Next slide, please. But the latest measurements, discoveries up at HARP have been this simple Brillouin scatter, where the electromagnetic wave decays into another electromagnetic wave at a slightly lower frequency and an ion acoustic frequency. So here's the pump wave, and here's the stimulated wave that's offset by the ion acoustic frequency. Next slide, please. So that's what it sounds like. What we've done is demodulated this signal to try to indicate what do the ion acoustic waves sound like in the plasma. Sounds like ducks quacking to me. Okay, next slide, please. That was when you take the beam and point it directly up the magnetic field line. When you tilt the beam to the vertical, you get the same mode produced, but it's offset by a higher frequency. That previous one was about 8 hertz. This was around 31 hertz. And this comes from the upper hybrid level in the plasma. What is interesting about this is this tells you what the electron temperature is in the media. Next slide, please. The measurement of that frequency and the constants in the media gives you the electron temperature with this formula. What you're doing is exciting ion acoustic waves. These ion acoustic waves are propagating at the ion acoustic speed given by this formula. So with the offset frequencies, you are given the ion acoustic velocity in the plasma, and then you can relate that to electron temperature. So we have electron temperatures around 3,000, 3,500 in the plasma, in the heated plasma, whereas the normal plasma has about 1,500 Kelvin. So we're elevating the temperature to a large degree by the high power radio waves. Next slide, please. Now, how many of you know Morse code? Okay, This is not Morse code. This is the ionosphere communicating O+. This is saying, I am composed of O+. It's this line right here is the ion cyclotron frequency. This is the O+ ions going around the magnetic field line. And if the mass of this increases, this frequency will drop. This is a spectrogram of the wave, and this is only produced if you tilt the heater beam more than 20 degrees off the magnetic field line. These were the ionacoustic frequencies, which is still here, that we got with a lower beam angle, but as soon as we went above 20 degrees, we got this mode being produced. Next slide, please. So we said, let's do an experiment. Let's tilt the beam here, and then tilt it over there, and see what happens. And as you see, immediately, this new mode is excited. So we have very strong confidence that this particular it happened again too. Electrostatic ion cyclotron mode is being produced in the plasma by the high power radio waves at the gyro frequency for the O+. Next slide, please. Okay, we're getting back to something a little more complex. Some of you know about ion-Bernstein modes. These are modes that are harmonics of the ion cyclotron frequency, covering a wide frequency range. So this is not a cascade. This is the electromagnetic wave producing a resonance at the second harmonic of the electron-Bernstein mode, then parametrically decaying into ion-Bernstein modes, and then coming back to us with offsets from the pump frequency at each of the ion-Bernstein frequencies. And let's hear what that sounds like. What we first of all get in the spectra is a mode at the ion cyclotron frequency. That dies off, and then you have this cascade of frequencies that are forming this cone right here. Why is this important? Because every time you see this, you see extremely bright air glow, and you can even make more plasma. You are resonating with the electrons, that the electrons are producing more ionization. Next slide, please. So this is this ion-Bernstein mode spectra we measure on the ground. Here's the pump wave, frequency plus or minus 500 hertz. Here's power. Here's the spectra at the plus or minus 10 kilohertz. This is his upshifted maximum, downshifted maximum lower hybrid wave. And here are the ion-Bernstein modes being produced here. What we have correlated is the optical emissions measured with by Todd Pedersen on the ground from, say, N2+. And when you're measuring N2+ emissions, you are actually making more ions because there's no N2+ in the F region normally. So you're accelerating electrons, colliding with N2, making N2+, and making the 4278 emission from N2+. And then here is the strength of this 200 hertz offset from this pump. Next slide, please. So what is happening is, besides making these electrostatic waves, you're resonating with electrons. These electrons then bump into the neutrals, making Aurora-like emissions at 6300, 1356, other wavelengths, and breaking down the neutrals. Next slide, please. So how does this resonance occur? It occurs at the second harmonic of the electron cyclotron frequency. The electrons are moving in this orbit, and if you're at the second harmonic, when the electron is here, it gets a kick, goes around a half an orbit, and this goes one full cycle and gets another kick over here. So it keeps getting a kick in place, it's electron cyclotron resonance, bringing up the energy to the point where it actually can ionize the media. Next slide, please. How do we know it ionizes the media? From the optics and doing tomography, Bjorn Gustafsson worked with Todd Pedersen on this, we see an enhanced region of optical emission in the heater beam below the normal reflection of the altitude. This is down at 150 kilometers altitude. It's a blob of plasma maintained or produced by the high power radio waves. The radio waves then go refract on this, and they make a ring. They make a ring around this blob, and that's where you get the optical emissions at higher altitudes. So if this occurs at the second harmonic resonance, this is very well understood in terms of the measurements. We can do it at will. And we think by looking at the plasma resonance and the stimulated electromagnetic emissions, we understand the process through cyclotron resonance. Next slide, please. So in summary, we've conducted a lot of very simple measurements. You just measure the spectrum of waves coming from the plasma and made some new discoveries. Stimulated lower hybrid waves have been seen for years. This stimulated Brillouin scatter was first reported by Noren et al., who were visiting HARP from Sweden. We then published some later works dealing with the SE emissions, looking at the emissions and seeing how it relates to the electron temperature. The electrostatic ion cyclotron wave measurement was recently published, and that actually tells us what the composition of the plasma. So let's say we have a sporadic E layer over Arecibo. All we have to do is turn on the high power radio waves, look for the emissions coming back, and we can then determine the composition of that sporadic E layer, where it's metallic ions or molecular ions. The ion Bernstein discovery was recently made, and it's correlated very strongly with the artificial air glow that's produced, a very strong artificial air glow. Next slide, please. Well, I've saved the best for last. What we're doing now is trying to hit the CNOV satellite with a big cloud of exhaust from the space shuttle. In order to do that, we asked NASA to fly the space shuttle with its engines pointed straight up. We then said, could you slow down the shuttle just a little bit so that when you fire the exhaust cloud comes up and intersects the CNOV satellite? And they were happy to do that. The reason is there's 2 or 3 more flights of the space shuttle. They only go to the space station and they have all this capability to do rendezvous, and they have it in place, the ability and the interest to do something complex. So they did it for us. On the CNOV satellite, we had a number of instruments. We showed some data from yesterday. But the most spectacular data came from the VFI, the electric field instrument on CNOVs. These 2 satellites passed within 90 kilometers of each other, but the cloud itself was timed, so the center was within 9 kilometers of the satellite, and the whole cloud expanded to a much larger diameter than that. Next slide, please. So what we're listening to now is the actual electric field measurements. Okay, when we turned on the engine, we heard a whistler. In other words, we launched a whistler 230 kilometers away, and then as the exhaust came closer and closer to the satellite, this is big cloud. You know, imagine being on the CNOV satellite, and you see this big cloud of exhaust coming toward you. Now you have to put on your seatbelt. Now you have to hold on to the So what is exciting about this is we had a magnetosonic pulse that occurred 6 seconds after we turned on the engine. So we're slamming the ionosphere with exhaust. It's building up this magnetic disturbance that it's actually probably what I call a fast MHD wave that hit the satellite. And then when the cloud intersected the spacecraft, we heard all of this turbulence from ionacoustic waves and maybe lower hybrid waves. Next slide, please. So we're now working on the theory of this, and Rob Pfaff, Peter Schuck, myself, and others are trying to see what kind of theory could cause such a phenomenon, what can produce the MHD pulse and the turbulence. We're looking at MHD theory, taking the continuity momentum equations, driving with a neutral wind. This is a hypersonic neutral wind from the shuttle exhaust, coupling through ion-neutral collisions, and you can separate into your usual slow MHD, alphane, and fast MHD waves. The fast MHD wave is the wave we saw promptly, and then of course the in situ generates maybe some of these other waves using these equations. So how does this relate to the natural environment? Well, ask Bob Lysak, propagation of alphane waves through the ionosphere. This is the same physics that produces PC1s, but we have a controlled way of studying it with the space shuttle exhaust. And MHD waves are quite interesting for the plasma community in general. So in summary, active experiments can really illuminate the physics of the ionosphere. With high power radio waves, we can cite both optical and radio emissions. We can make irregularities visible that are normally not so visible. We can measure the ion composition, the ion sound speed, and plasma temperature. and also the conditions for resonance acceleration of electrons to make artificial air glow and to break down the neutrals. The rocket exhaust is a wonderful remote sensing tool. We get enhanced glow that make plasma regularities show up better. We can trigger instability with ion beams, produce small-scale field line irregularities, large-scale plasma bubbles, and we can stimulate plasma wave modes. These are MHD modes that propagate for long distances, and then local enhancements in plasma wave turbulence. So I just want to say, in summary, I think active experiments very well complement the other passive remote sensing tools that we've commonly used. Thank you.